El Capitan will be the Department of Energy's National Nuclear Security Administration's first exascale computer. In terms of its raw performance, it will be 16 times more powerful, at least, than our current flagship machine, Sierra. El Capitan is a very complex scientific instrument. It is similar to, say, the Hubble telescope. It takes expert people developing expert software tools to make it run. Although El Capitan will be unique, it is one of a long history of supercomputers that have been fielded here at Lawrence Livermore National Laboratory. As a result, we have a long history of developing open source software that has been run on many different architectures of computers.
So we run two kinds of machines here at Livermore Computing. One is the commodity technology systems, which are our regular clusters, and one are the advanced technology systems, which are the machines like Sierra and El Capitan. El Cap is the first advanced technology system where we're running an entirely Livermore-provided software stack on it.
We will run TOS, an operating system that is developed here at Lawrence Livermore National Laboratory. On top of that, we'll run SCR, the Scalable Checkpoint Restart. On top of that will be Flux, our scheduler that will help schedule each unique job to run on a certain percentage or partition of El Capitan. When a user on El Capitan is interested in answering a particular question that they have to go through several steps in order to get to the answer they're looking for. The first thing they have to do is say, what's the appropriate piece of software that I need to use in order to answer that question? From there, they have to define the appropriate input parameters. They have to say, what does that piece of software need to ingest in order to answer the question that I have? Then they will submit that job to El Capitan. They'll run the job on El Capitan. That will rely on a scheduling software like Flux that we develop here.
Flux was extended for this purpose to be able to co-schedule both the compute nodes and the storage resources for your job. And then at the end of the job, when it completes, that data can be automatically migrated off.
I/O refers to the input and output operations of applications. That means that they read in data, their initial conditions for the problem they're trying to solve, and then periodically through the simulation, they will output data that shows the intermediate results of the simulation, and then finally at the end, a final result.
So the rabbits are a new exciting bit of functionality that's being added to El Capitan. This is something we haven't done on previous systems before, but what they allow is a near-node local storage solution that can be used on the system. So applications can dynamically request the storage resources they need, have them be made available as part of their job, and then have whatever data they've generated as part of their job be automatically migrated off when their job is done to the larger file system.
As a researcher, the rabbits are hugely exciting to me because I see them as a stepping stone in getting to where I/O performance is on par with compute performance. One of the tools that we will run on the Rabbit nodes is called SCR, which is the Scalable Checkpoint Restart Library, where they save intermediate state from their simulation throughout time so that if there's a failure of a compute node, for example, or something else, the state is saved and they can restart. The advantages here are that the Rabbits will be private to their job, and so they won't have as much interference from all the other jobs running on El Capitan at the same time, so they get a much better performance experience.
In HPC, people want a lot of flexibility with how they deploy their software. You might want to build something, with different compilers to see which one performs better. Or one piece of software may have requirements on how another one is built. And there was no package manager before SPAC that could really satisfy those needs, right? That would allow you to have these sort of combinatorial installations of things. SPAC gives you the configurability while also wrapping the software deployment process in like this reproducible framework.
One thing that is very important to our application developers and our application users is portability. It's very important that although El Capitan is very unique, the software that runs on it is capable of being run not only on El Capitan, but on many other supercomputers as well. Because of that portability, it's enabled a smooth transition for our application developers.
El Cap was brought in to support the mission of stockpile stewardship and of weapon modernization for the U.S. nuclear stockpile. And so most of what El Cap is running is going to be our traditional stockpile simulation workload. I'm also excited about the software stack and just continuing to see packages like Flux deployed on a really, really big system and seeing SPAC perform for the code teams for the program.
El Capitan, Tuolumne, and other systems like it will allow us to answer questions we haven't yet thought to ask in areas like bioresilience, drug discovery, computational medicine, astrophysics, climate modeling, materials science, a plethora of scientific disciplines. The scientific exploration that will be possible on these types of machines will be at a fidelity, a resolution, a level of detail that's not been possible in the past.